so this is actually a generalization of the backpropagation formula we derived. Because in our backpropagation formula, we can actually pretty easily write the collection of constraints into a single constraint, right? We can, so in our previous case, we looked at, so in the previous case, we had a u k plus 1 is equal to gk of uk and s, right? We can simply write our big U as a collection of u1 to un, right? And my big G is just a u1 minus g0 u0 s and u2 minus g1 of u1 s, etc. to un minus gn minus 1 of un and minus 1 s. Right, so I can simply write it in such a way. And then the adjoint equation becomes actually the same equation as we were solving, except for if you look at the structure of dg du. It is like what? If you look at the G. The first row is the derivative of the first equation with respect to u, which is 1 here, or identity if it's a vector form, and all zeros, right? Because the first row depends not on any of the later on equations. Now the second row, I have I here and something here, right? But also all zeros. The third row, I have identity here, something on the left, and all zeros. So basically what I get is I get a lower diagonal matrix with identities on the diagonal, with ones on the diagonal, right? That means when I want to solve this equation, actually solve the transpose of this equation, where should I, how do I, okay, so how do I solve the transpose of a lower diagonal matrix, which is an upper diagonal matrix? Backward substitution, right? So if I solve a lower diagonal matrix, it's forward substitution. When I solve the adjoint, which is the transpose of a lower diagonal matrix, I do backward substitution. That's why it's backpropagation. We are starting from the end of these u hats and propagate forward. It's simply because we are solving actually an upper diagonal matrix. And that matrix can be simply derived with these few lines of mathematical derivation, right? And this is actually generally how do you derive the adjoint for an general implicit or explicit algebraic constraint. Questions? Yes.
So can we do this if J is a function of S?
So if, good question, if J is also a function of S. Okay, so then delta J would be this plus partial J partial S times delta S, right? And when I keep deriving, I would just carry this term. So I would just add a partial J partial S inside this. So my gradient of my total derivative of J to S would be including the adjoint term, u hat transpose times dgds, plus an explicit partial derivative of J to S. So let me actually, it may be a little bit confusing. Let me write it down. So usually that's how people write it. dj ds is equal to u hat partial G partial S plus partial J partial S. So this partial G partial S is the partial derivative for a fixed u. if you fix the solution u and just look at the explicit derivative of j to s, this is what this is. While on the left hand side, it is the derivative of j with respect to s, including the consideration that u depends on s. Is you change your s and look at how j changes by the combined effect of the changing s and changing u due to a change of s. All right, this is what happens if j actually explicitly depends on s. All right, this is actually the case if you have an airplane and look at the drag or lift, because even if the flow solution stays exactly the same, changing the geometry is actually going to change the forces. So this is usually actually the case. J explicitly depends on s.